We have been discussing about vector spaces in linear algebra, and next we are going to see a special kind of vector spaces which are called inner product spaces. We have seen that a vector space is a set together with two operations. One is called vector addition and the other one is called scalar multiplication. These two operations satisfy 10 properties, and in addition to that structure, suppose we are able to define a product among the vectors which is called an inner product, then the vector space together with this particular inner product is called an inner product space. An inner product is basically a generalization of the dot product of vectors. Let us recall what was the dot product of three-dimensional vectors. Suppose we have two three-dimensional vectors, say a bar and b bar. Then a bar dot b bar was defined as the components of a bar has been taken as a1, a2, a3. That is, a bar is equal to a1i plus a2j plus a3k, and b bar is similarly defined like this. Then their dot product has been defined as a1 times b1 plus a2 times b2 plus a3 times b3. So this was the definition of dot product of two three-dimensional vectors. If dot product is defined like this, then we can see that a bar dot a bar is equal to a1. This b1, b2, b3 has been replaced by a1, a2, a3 itself. So it will be just a bar dot a bar will be just a1 square plus a2 square plus a3 square. And we know that in three-dimensional geometry, the length of a vector is the root of a1 square plus a2 square plus a3 square. Hence a bar dot a bar is nothing but the square of the length of vector. So there is an association between the dot product of a vector with itself and the length of the vector. Geometrically, we can see that if a bar is this particular vector and b bar is this vector, and suppose the angle between them is theta, then you know that a bar dot b bar can be written as the length of a, which is a number, into length of b, which is also a number, which is a positive number, into cos theta. And since this theta is the angle between the vectors a bar and b bar, we can say that a bar is perpendicular to b bar when the angle theta becomes 90 degree. Or you can say that a bar dot b bar is equal to 0 when a bar is perpendicular to b bar, because cos 90 is equal to 0. Conversely, we say that two vectors are perpendicular if their dot product is equal to 0. So using the dot product, you can also define the concept of an angle between two vectors and the concept of perpendicularity. Now regarding the properties of scalar product, one can see that a bar dot a bar is equal to a1 square plus a2 square plus a3 square, and being the square of real numbers, this quantity will be always greater than or equal to 0. So a bar dot a bar is greater than or equal to 0. By mistake I wrote a b bar here. It is a bar dot a bar. A bar dot b bar can be non-positive or negative also. Now you can see that a bar dot a bar is equal to 0 only if the sum of these squares are 0. That means each a1, a2, a3 all should vanish. So a bar dot a bar is equal to 0 is possible if and only if a bar is equal to 0 vector. So for a 0 vector only the length can be 0. Now distributive property is also there, that is a bar plus b bar times c bar, that is dot product with the c bar is equal to a bar dot c bar plus b bar dot c bar, and alpha times a bar dot b bar is equal to alpha is a scalar, then this alpha will come out of this dot product, that is alpha times a bar dot b bar. And you can also see that the dot product of two real three-dimensional vectors is commutative, that is a bar dot b bar is equal to b bar dot a bar. Okay. Taking consideration of all this, we generalize the concept of dot product to a vector space. As you know that the three-dimensional vectors form a vector space over the collection of all real numbers, you can use this concept to define a product between two vectors, and that product is called an inner product. So in some vector spaces, a product like the dot product can be defined. So essentially here this dot product between vectors a bar dot b bar has been denoted by a new notation, that is a bar inner product with a b bar. So this is read as inner product of a bar b bar. It is actually equivalent to the dot product of a bar and b bar if we consider three-dimensional vectors. Inner product is actually a function. It can be defined only if two vectors are present. So one vector has to be coming from this first v and second vector also coming from the same v. So it is a function from v cross v to k, r or c, depending on which type of scalars you take. If it is real scalars, k can be real, or otherwise it is complex. A function from v cross v to k is said to be an inner product if it satisfies these properties, that is inner product of v with itself should be greater than or equal to 0. Actually, it should represent the square of the length. That should be a positive number. And the inner product of v with v itself should be 0 if and only if v equal to 0. That means length is equal to 0, or the square of the length is equal to 0 whenever the vector is 0. v1 plus v2 inner product with v3 is equal to v1 inner product with v3. That is the distributive property holds. And v2 inner product with v3, their sum. Now alpha will come out if you take an inner product of two vectors in which one vector is multiplied with an alpha. So alpha times v1 v2 is equal to inner product of alpha with v1 times v2, or this alpha can be here also, but when it comes from the second coordinate, there can be a conjugate. There will be a conjugate if you take complex numbers because of the last property. Inner product of v1 with v2 need not be equal to inner product of v2 with v1. It can be the conjugate of v2 with v1. If the space is complex, you have to take the conjugate. If it is a real space, that is, if the scalars are considered to be real numbers, you can just say that v1 inner product of v1 with v2 is equal to inner product of v2 with v1. Scalar product or the inner product is commutative in that case, if it's a real vector space. If it's a complex vector space, inner product of v1 with v2 will be equal to the conjugate of inner product of v2 with v1. If this is a plus ib, this must be a minus ib. So their conjugate only will be equal. Okay, if on a vector space you can define an inner product like this, then V is an inner product space. For example, on Rn, you can take inner product of U with V to be that A1 B1 plus A2 B2 plus A3 B3 plus etc. plus AN Bn. That is, it's just an extension of the dot product in the case of Rn. Now, if it is Cn, due to the last property, this property, you should have a conjugate coming into picture. Otherwise, you will not be getting this positivity and the second property also. So you have to define in the complex case, if you are taking n tuples of complex numbers, the inner product of u with v has been defined as sigma ui vi bar. That is u1 v1 bar plus u2 v2 bar plus u3 v3 bar etc. plus un vn bar. And on function spaces, we can define the inner product of two functions using the integral. And the integral is integral a to b f of x g of x bar should be there if it is complex. It should be the conjugate of the second function. The first function should be multiplied with the conjugate of the second function and integrated from a to b. Let us see an example. Suppose I take R3 and take two vectors like this, 1, minus 2, 3. So I am taking R3 as my vector space or inner product space. Then this inner product with the next vector 2, minus 1, 0. This inner product is defined as, it's basically the dot product 1 into 2, which is 2, plus minus 2 into minus 1 is 2, plus 3 into 0 is 0. So the inner product is 4. And if it is a complex case, that is C3 and all if you take, so then the vectors can be complex vectors, that is 2i, then 1 plus 2i, then third component can be 2. Complex real numbers are also complex numbers, right? So suppose this is 2 minus 2i and this is 0 and this is 1 minus I, then the inner product is going to be 2i times the conjugate of the first coordinate of the second vector, that is minus 2i bar plus 1 plus 2i times 0 plus 2 into 1 minus I conjugate. So this is going to be 2i times plus 2i, that is minus 4, plus the second one is 0, plus 2 plus 2i will come. So altogether it is minus 2 plus 2i. Okay, inner product of two different vectors can be complex numbers or real numbers, negative numbers also. But if you take the two vectors as the same, then the inner product should be greater than or equal to 0. Okay, these are some examples. And if you want to take the collection of C0, 1, that is a vector space of continuous functions. So you have two vectors, sin x and cos x are elements of this vector space. Then the inner product of sin x and cos x can be defined like this. Inner product of sin x with cos x is equal to integral sin x into cos x conjugate is cos x itself, integrated from 0 to 1. So integral of 0 to 1 sin x cos x dx. That will be giving you a number. So that will be the inner product of sin x and cos x. Thank you.